Hey everyone! Today we're digging into something that seems simple on the surface, compressed gas. We all learned the basic rules in school, but what happens when those neat textbook formulas get thrown into the high-pressure, high-stakes, real world? Well, as we're about to see, that difference can be pretty explosive.
And really, that's the question at the heart of all industrial safety, isn't it? We use compressed gases to power our world, in everything from heavy-duty compressors to pneumatic systems. But that same incredible power, if you don't fully understand it, carries a massive risk. So let's break down exactly why.
Okay, so the biggest difference between a liquid and a gas is pretty straightforward. Liquids, well, you can't really squash them. They're incompressible. But gases, they're elastic. You can squeeze them. And that very property, their compressibility, is what we harness for power. But it's also the source of some pretty hidden dangers that we're going to uncover right now.
To really get a grip on how gases work, we have to start with the foundation, right? And that's the ideal gas law. This is the first thing we're all taught. It's the model for how a perfect gas should behave under perfect conditions.
And the formula itself, it's pretty slick. Pressure times volume is directly related to temperature. It's our theoretical baseline, but it makes a huge assumption. It assumes we're in a perfect world where all the tiny gas molecules just float around and never ever interact with each other.
Now, out in the field, for a lot of your day-to-day work, this big law gets simplified down to something called Boyle's law. It's a fantastic rule of thumb. It's basically a special case where you assume the temperature stays constant. And all it says is if you change the volume, the pressure is going to change in a nice, predictable, opposite way. Let's see what that looks like. So let's just imagine we've got a container full of gas. This is our starting point. We'll call it 100% volume and 100% pressure. Simple enough, right? Okay, now according to that simple rule, Boyle's law, if we squeeze that gas and cut its volume in half, down to 50%, then the pressure should just, perfectly double to 200%. A very neat and tidy calculation.
But hang on a second. That whole neat and tidy calculation rests on one massive assumption, that the temperature doesn't change a bit. But is that really what happens when you rapidly squeeze a gas into a tiny space?
And this is where textbook theory just smacks right into the wall of reality. This is where 4 decades of on-the-job experience comes in. There is a golden rule for anybody working with pressure equipment, and it's this. When you compress a gas fast, you don't just get more pressure, you get a ton of heat.
So here's the absolute key. When you compress a gas, you're forcing all those molecules closer and closer together, and all that energy you're putting in has to go somewhere. It gets released as thermal energy, as heat, which causes a massive and immediate spike in temperature. This is the hidden variable that the simple laws just completely ignore.
And this is why we can't ignore it. This isn't just some, minor detail for the physicists. If your design calculations miss this massive heat spike, you're not accounting for the thermal expansion it causes, and that puts an unbelievable amount of stress on the steel, on the seals, on everything. It leads to one place: catastrophic equipment failure.
The bottom line is this. In the real world of industrial gases and high-pressure systems, the stakes are just way too high. That perfect, ideal equation, it just breaks down. It's not just inaccurate, it's dangerous. It's no longer a reliable guide.
So why does it fail? Well, it's all about physics. Think about it. At low pressures, the gas molecules are like strangers in a giant empty room. They've got tons of space, they rarely bump into each other. But when you crank up the pressure, you're shoving them all into a tiny, crowded elevator. Now they're bumping into each other, they're pushing off each other, and all those little interactions fundamentally change how the gas as a whole behaves. So if we want to engineer systems that are actually safe in this messy, chaotic, real world, we need a law that actually accounts for that reality. And that, my friends, is where the real gas law comes into play. Just look at them side by side. The formulas look almost identical, right? But the real gas law has this one extra letter in there, one tiny variable that makes all the difference in the world, the letter Z. That single factor is our bridge from clean theory to messy reality. So what is Z? It's the compressibility factor. And the best way to think about it is, it's a reality check. It's a correction value that engineers calculate to account for all those molecular forces and, crucially, those temperature spikes that the ideal gas law just pretends aren't happening. And that really brings us to the most important takeaway here. Anybody can memorize a formula from a textbook, but a true pressure equipment engineer, they're the ones who understand the limits of that formula. They know when the theory stops and reality begins, and they know how to correct for it. That knowledge, that's what keeps people safe. So as we wrap this up, I want to leave you with this one thought to take back with you. The next time you look at any high-pressure system,
Ask yourself this question. Is its safety built on a perfect, clean theory, or is it truly built to handle the heat, the stress, and the chaos of the real world? Thinking about that question, well, that can literally save lives. Thanks for tuning in.